This presentation introduces our CVPR 2026 work titled ManifoldNeuS, Manifold-aware view optimizability for pose-free neural surface reconstruction. Multi-view 3D reconstruction is a cornerstone problem in computer vision and graphics. The traditional 3D reconstruction is usually performed with known camera poses, often estimated by structure from motion before geometry optimization. However, this preprocessing may fail in textureless, repetitive, or illumination-varying scenes. Pose-free reconstruction removes this assumption. Camera poses are unknown and must be recovered together with the surface. This setting is more practical for real-world capture, but also significantly harder. Our work focuses on joint pose and geometry optimization. Given unposed images, we optimize camera extrinsics together with an SDF-based scene representation through differentiable rendering. The critical challenge is that pose and geometry errors can reinforce each other, making the joint optimization highly ill-posed. When poses are accurate, multi-view rays provide consistent geometric constraints, allowing the zero-level set to converge to the true surface. However, when poses drift, these ray constraints become inconsistent, which distorts the SDF geometry and leads to fragmented surfaces. Existing pose-free 3D reconstruction methods can be grouped into three categories. First, transformer-based methods perform feed-forward pose and 3D prediction, but depend on large-scale supervised training with pose-annotated data. Second, 3D Gaussian splotting-based methods benefit from efficient rendering performance but are limited by discrete primitives and initialization-sensitive pose estimation. Third, neural implicit methods offer continuous surface modeling with high geometric fidelity, but joint optimization is sensitive to pose errors. Our work follows the neural implicit direction. We find that most pose-free neural surface reconstruction methods adopt uniform training, treating all views equally despite differences in per-view optimizability. This uniform strategy leads to easy view bias problem. Specifically, easy views usually have rich textures and strong overlap, allowing them to converge quickly and dominate pose and geometry updates. In contrast, hard views often contain weak texture or limited overlap, so they tend to be under-optimized in the early stages. However, these views can be structurally valuable because they provide new global coverage. This imbalance causes pose drift and incomplete geometry recovery. To verify this phenomenon, we quantitatively analyze the training behavior of easy and hard views. Here, we define easy views as the views with the highest overlap and hard views as those with the lowest overlap. The first two plots show that easy views consistently have lower rotation and translation errors throughout training, which indicates faster convergence. The third plot shows that they also generate larger pose gradients. The fourth plot further confirms that these views contribute a large portion of the total pose gradient norm, revealing clear local gradient dominance. The spectral distance curve in the last plot shows that global coverage improves slowly, meaning that optimization remains concentrated around easy, highly overlapping views, while views that could expand the global geometry are underemphasized. These observations motivate our formulation of view optimizability. Our key idea is to explicitly model per-view optimizability from two complementary perspectives. The first is immediate fitness, which measures how effectively a view can accelerate convergence and refine the currently optimized geometry. This is captured by local multi-view consistency, which we call local constraint strength. The second is long-term coverage gain, which measures how much a view expands topological coverage and helps recover unexplored geometry. This is captured by global topological coverage. By combining these two factors, per-view optimizability becomes a state-aware signal for controlling joint optimization. The overall framework is summarized as follows. Given multi-view image collections without known camera poses, we first compute a manifold-aware view optimizability score by balancing local constraint strength and global topological coverage. Second, we use per-view optimizability as a control signal for 3 reconstruction mechanisms guiding stable joint pose and geometry optimization. Next, we will explain how per-view optimizability score is computed. The score combines two complementary terms. The first is local constraint strength, which measures how easy a view is to optimize. We first compute pairwise feature correspondences and build a co-visibility matrix. A view with stronger local constraints has higher co-visibility with other views, providing more reliable geometric constraints for stable early optimization. The second is global topological coverage, which measures how worthwhile a view is to explore. We construct a view graph from the co-visibility matrix and apply spectral embedding to approximate the view-coherent manifold. A view that is farther away in this manifold space is more likely to introduce new structural information beyond the regions that have already been optimized. By balancing these two terms, we can select views that are not only easy to optimize, but also structurally valuable for completing the global geometry. After computing per-view optimizability score, we use it to guide reconstruction through 3 mechanisms. The first is view scheduling with dynamic refinement. We start with reliable anchor views that have strong local constraints, and then progressively introduce successor views to expand topological coverage. This avoids optimizing all views at once and reduces instability in the early stages. The second is gated positional encoding. It adaptively modulates frequency activation, reducing premature high-frequency interference during early pose estimation while still allowing fine details to be learned later. The third is anti-score loss weighting. Views with lower score value are assigned stronger supervision, so the optimization is not dominated by easy views. By integrating these 3 components, we achieve a final 3D reconstruction with accurate camera poses and high-quality scene geometry. We evaluate on D2 dataset and compare against for representative baselines. The evaluation considers both pose estimation and reconstruction quality. This slide summarizes our implementation details. This slide presents the main pose estimation results. Compared with existing baselines, our method achieves significantly lower rotation and translation errors, demonstrating that our method can recover accurate camera poses from unposed image. The pose visualizations further confirm this improvement. Our method closely matches ground truth camera poses, while baselines converge to suboptimal or noisy estimates. This slide evaluates reconstruction quality. The results show that more accurate pose estimation leads to better geometry reconstruction. Baselines with unstable poses produce noisy, incomplete, or distorted surfaces. In contrast, our method recovers more complete and coherent geometry. We also evaluate novel view synthesis. The results demonstrate that better pose surface consistency leads to more reliable rendering from unseen views. Compared with the baselines, our method reduces structural artifacts and produces sharper, more geometrically consistent renderings. We evaluate robustness under sparse view settings. Even with only 10 views, our method achieves better pose accuracy and geometric fidelity than the baseline. In terms of efficiency, our method offers a favorable trade-off of accuracy and efficiency. We conduct a series of ablation studies to validate the design choices and hyperparameters in our method. This slide evaluates the contribution of each component. The results show that all components contribute synergistically, delivering robust pose recovery and high-fidelity reconstruction. We ablate the balance between the local and global terms in view optimizability score. A high alpha value overemphasizes local constraints, selecting reliable but clustered anchor views. A low alpha value improves coverage but weakens local support and reduces anchor pose accuracy. The visualizations on the right also show this behavior clearly. The full score with alpha equal to 0.65 achieves the best trade-off results. This slide highlights the effectiveness of our manifold-aware coverage design. We compare our view optimizability score with farthest point sampling and also evaluate to coverage metrics, Euclidean distance on the co-visibility matrix, and distance in the spectral embedding space. Results show that spectral embedding manifold coverage improves global connectivity without sacrificing local optimization stability. We also vary the number of anchor and successor views. The selected configuration, 30% anchors and 20 successors per round, balances pose accuracy and optimization efficiency. This slide validates the design of gated positional encoding and the training losses. For positional encoding, the ablation shows that frequency-aware modulation is important for preserving high-frequency geometric details, while temporal modulation further stabilizes optimization. The scaling factor with lambda equal to 0.3 achieves the best balance results. For the training losses, the ablation shows that the normal loss helps reduce both rotation error and translation drift, while the depth loss mainly improves rotational accuracy. This slide shows 360-degree mesh comparisons across multiple digit scans. With continuous rotating viewpoints, this visualization makes it easier to observe not only local details, but also global surface completeness and structural consistency. Baselines often suffer from fragmented geometry, missing regions, or failed reconstructions. In contrast, our method recovers more complete and coherent meshes. Its quality is close to NeuS with ground truth poses, showing that our pose-free optimization can achieve strong surface reconstruction quality without relying on known camera poses. To conclude, we identify easy view bias as a key challenge in pose-free neural surface reconstruction. To address this issue, we propose view optimizability score, which jointly models local constraint strength and global topological coverage to measure the optimization value of each view. By integrating the view optimizability score into the reconstruction pipeline, our method achieves stable joint optimization from unposed images, improving both camera pose recovery and surface reconstruction quality. We hope that view optimizability will inspire future research on pose-free neural surface reconstruction. Thank you for watching. If you are interested in the details, please refer to our paper and supplementary material.